Okay, so in the last section, we talked about the events at the synapse. I'm going to review them because they're important. So that's those 7 steps listed on page 49 of the book, or right here in front of us. The sequence of events. Number 1, action potential arrives at the presynaptic terminal. Number 2, presynaptic terminal is depolarized, causing voltage-gated calcium channels to open. Number 3, the synaptic vesicles move towards their release site. That is triggered by the movement of calcium. Number 4, neurotransmitter is released in the synaptic cleft. Number 5, neurotransmitter diffuses across the synaptic cleft. Number 6, neurotransmitter binds to the postsynaptic receptor. And number 7, the membrane channel or the membrane receptor changes shape, causing either an opening of ion channels or an intracellular cascade of events. Okay? Those are our 7 steps that you should know. The other thing that you should know is that the amount of neurotransmitter that is released at one time depends on the strength and duration of the stimulus, as opposed to the all or nothing response of an action potential. So the action potential, it doesn't matter if you have a huge stimulus or the minimally effective stimulus for a threshold. It's just if you have enough stimulus, an action potential will be created. With the neurotransmitter, if you have a stronger stimulus, more neurotransmitter will be released. Okay, so more receptors will be binded and there'll be a bigger reaction and more opportunity to create an action potential in the postsynaptic cell. Okay, so there are a couple little videos here about events at the synapse, and you can certainly look at those at your discretion. So we're going to talk about postsynaptic potentials. So what happens at the postsynaptic cell depends on the receptor. Okay, so some postsynaptic potentials are excitatory. They're going to excite the postsynaptic cell. They are going to hopefully trigger another action potential and fire off that cell. Okay, so they are going to depolarize the postsynaptic membrane. So when we remember that depolarization is when the membrane becomes less negative than its resting state. So in an excitatory postsynaptic potential, or Ipsp for short, local depolarization on the postsynaptic membrane, neurotransmitter opens calcium or sodium gates, it depolarizes that part of the membrane, and it's an excitatory response. It excites that. It causes, hopefully, that 15 millivolt change to fire an action potential. So we said a little bit earlier that the stronger the stimulus, the more neurotransmitter is released. So the more neurotransmitter there is in the cleft, the more receptors are going to get stimulated, the more local potentials we're going to get adding up, and there's a higher chance of there being an action potential firing. It causes the excitation of that neuron. Okay? So the opposite is an inhibitory postsynaptic potential, or Ipsp. So that postsynaptic potential causes local hyperpolarization on the postsynaptic membrane. So if you remember from chapter 2, hyperpolarization is when the cell membrane becomes more negative than its resting state. So it's sort of related to that refractory period. In the relative refractory period, when it's hyperpolarized, it's more negative than the resting state, so it takes a bigger stimulus to generate an action potential. So with an inhibitory postsynaptic potential, there's a local hyperpolarization of the postsynaptic membrane. The neurotransmitter binds to a receptor that opens calcium channels, so it can become more negative inside the cell, or potassium, so potassium, which has a positive charge, can exit and it becomes more negative inside the cell, so that's hyperpolarized. And it causes an inhibitory response. There's less chance that that neuron's going to fire. Okay, so an excitatory postsynaptic potential causes depolarization of the postsynaptic membrane. It makes it less negative than its resting state. An inhibitory postsynaptic potential causes hyperpolarization of the postsynaptic membrane. It makes it more negative than its resting state. So it's inhibitory because there's less of a chance of firing off an action potential when the membrane is hyperpolarized. Okay? So those diagrams are straight out of the book, just like all the diagrams. Well, not every single one of them, but there you go. There's a little 12-minute video about postsynaptic potentials. Again, you can watch it or not, as you prefer. So there are also some PowerPoint slides about the postsynaptic potentials. They go over the same stuff we just talked about. An excitatory postsynaptic potential is local depolarization, and inhibitory is local hyperpolarization. Okay? So that's it for this section, and then in the next section we will talk about presynaptic facilitation and presynaptic inhibition.